point of discontinuity. So limits can be used to describe how a function behaves as an independent variable moves towards a certain number. We usually move towards, if it's a removable point, we move towards that number. We can move towards infinity, like how does your n behave? If your graph goes like this, so as x approaches infinity, what happens to your y? It's going to approach this asymptote. We did these. We had asymptotes. We did horizontals. We did vertical asymptotes. We did points of discontinuity. That's this revisited. But now we're calling them as limits. And when we do a series of limits, we approach them from both sides. If there is an opening there. So, for instance, let's talk about one that you might be a little bit more familiar with. Way back when we did functions, we had this little rational function, and we said factor this. It's also like a good review for you guys. And we said, what happens to the factor that is common in both numerator and denominator? It cancels out, and this becomes our point of discontinuity. So we're left with, after we factor, so if we find this point of discontinuity, this should come back to you. And we need to find its y value. We then plug this into here, because we couldn't plug 1 into there, -1 into there, because it wouldn't exist. It would give us a 0. So we say, what is the limit as x approaches -1? It can't be -1, because -1 won't work. So we took this out. We said this is going to be our little point of discontinuity, and then we plugged it back into when after we reduced it. So we got the y value. So if this point did exist, we had a point of this, and we called it our point of discontinuity. Remember doing this with your point of discontinuity? Way back when we were doing functions and rationals and all of those guys, and we had asymptotes, we had rules for asymptotes. We're going to revisit those rules as well. But the idea is you could actually, when you graph this, it looks like it's continuous. But if you graph this and you set your table around -1, you should be able to, from both sides, see where this is going to approach. So both sides are converging at the -2. So if I was going to remove this point, if this was removable, I would remove this point. I would fill this in at -1, -2. So what we're saying is, if you found the limit as x approaches -1 from this side, then the value of y would be -2. I can't plug this into here. I can't plug in x equals -1 in here, because that will give me a denominator of 0. So what we did, probably September, October, probably October-ish we were doing this, is we found our point of discontinuity, and we reduced it without the point of discontinuity. And then we were able to work from there. Do you guys remember doing the point of discontinuity? Slightly? It'll come back to you. So this is a good review, actually, to bring your functions back, because we did them so long ago. So all this is saying is, I can approach it from both ends. And looking at it graphically, I should be able to find my point. Now, not all things have limits. This, I can clearly see if I met halfway, I met from the -2 side to the 0 side, from the x, I could come together at one point. Not all things will come together, so sometimes the limit does not exist, which is when you hear that term that a limit does not exist. In this case, this limit does not exist. There's no way that you could join those by filling in one little point. This guy approaches one value of y, this side approaches another value of y at when x is 2, and there's no way to join them. So this limit does not exist. And sometimes we're going to call this a jump discontinuity, it jumps. So there are other little names that we'll call these guys. So sometimes the limit does not exist. In this case, here's a piecewise function, and this is a good review for piecewise. If x, you're doing y equals 2 and y equals 0. When x is not 3, y is equal to 2. When x is 3, y is equal to 0. So you can see what happens to your graph. That point can be filled in here, but this point is not going to count. So we can't count that point, but with this one, it can actually converge when it is 2. It only can be on that same line. So if I can find a point that I can actually fill in and make a complete line, I have a limit. This point isn't going to help me. It's off the line. So the limit for this one has to be right here, where we fill this in. Has to be at 2. We're going to do some more of these. These are just solving them graphically, and we're also going to look at algebraically today. This one, we say without bound. It has no limit, because what happens as x approaches 0 from either side, this guy is an asymptote down the middle. It will never, never touch that when x is equal to 0. So what happens, it gets closer and closer and closer from both ends, but never, never converges or reaches it. So this we say without bound. There's no bound to this. It will never stop. It will never converge at one point, right? Doesn't that asymptote means it'll get closer and closer, but never touch it? Okay. So this is basically what we're revisiting your limits right now. And graphically, you can look at them. You can clearly see a point when it's removable, and we call this our point of discontinuity. If we can't remove it, it jumps. There's no way it's going to meet. It has no limit. And a limit can fail from these three things. This is important to know. They approach a different value from the x and the right of whatever their limits as they reach 2, as they reach 0, whatever number. So this guy approaches a certain number, 1. This guy approaches a different number, -1. And it never can approach the same number. It'll increase and decrease without bounds, and it oscillates between two fixed values. It'll do like a step, and it'll never meet. So sometimes the limit does not exist, and sometimes we can remove that limit. It approaches a certain number. Does it kind of make sense to you a little bit? We did these before. We found asymptotes, we factored, we found points of discontinuities. We just didn't call them limits. And to do this, we can do a direct substitution, see if the limit does exist. Sometimes it is a filled-in point. It could be at any point we're looking for a limit. So it's the y value that x value gives us. We can find the limit of a rational. We can use cancel techniques. This is your factoring techniques. Find your point of discontinuity. You can use your technology, put it in your calculator, look at your table. And you have one-sided limits, and we'll look at those a little bit separate. So just a little variety on this, and it's going to all look familiar to you, and you're going to say, but we did this before. We did all of this before. We're just recalling them so that when you walk into calculus and Mr. Nee starts using the word, what limit does it reach, or as x approaches infinity, what's the limit, you'll say, oh yeah, I know that. So this guy, when we look at this, does it have any domain restrictions? Is there any value of x that can't be used? So anything you plug in is going to return a y value. So always look at your domain restrictions. This has no domain restrictions. I get a nice little parabola. So all I have to do as x approaches 4 is find out what is that y value. You could do it in your graph. You could substitute it in directly. 4 squared plus 2 times 4 minus 5. 16 minus 8 gives you 8, minus 5 is 3. So your limit is 3. Thank you. Oh, what did I do wrong? Oh, it's a plus. This is a plus, sorry. 16 plus 8 is 24, minus 5 is 19. Put it in your calc. You can graph this, take it off your table. You could directly substitute it in. Always look to see, does it have a domain restriction? As soon as you know if it has a domain restriction, you know it's jumping somewhere. It's going to jump over one number, or hit an asymptote, or do something. So if it has no domain restriction, you can plug it right in. And that's how we write it. As the limit, what's the value? As x approaches 4, it's your y value. Sometimes it's just called the value of the function. Your y value is called the value of the function. So sometimes it'll say, what is the value of the function when? And it's your y value. Okay. Cancellation, we just looked at cancellation a minute ago. Graphically, this is your point of discontinuity. This is your factor. Okay, factor the numerator. And usually, if you're going to be able to reduce, that's probably one of the factors down there. When you take this out, this is your point of discontinuity. So when x is negative 3, so see it's asking what's happening when it's negative 3. If you try to directly substitute it in, it'll make your denominator 0. Because where is my domain restriction? My domain restriction says, well, the denominator can't be 0. So my domain restriction says, oh, you have a domain restriction at negative 3. You can't use negative 3. So it's either going to hit me at an asymptote, or it's going to hit me at a point of discontinuity. A point of discontinuity is removable. An asymptote is not. And we'll do a case of an asymptote when we actually hit without boundaries, technically. So if you wanted to graph this guy, and this is what I mean if you want to confirm this on your table. Move it back to functions. If you want to graph this guy, I'll make an attempt to graph and we'll see what it looks like. Sometimes this works really, really well, and other times not so well. Okay, you guys can graph this. And when you look at this, set your table to start at negative 3. This is the point where negative 3 says error. So set your table to start at negative 3 and change your table, put 0, 0, 1. And you can see that they're going to converge at the same point. And that point is negative 5. Algebraically, how we find it? We take out our point of discontinuity, and we're left with this, after we've factored out our point of discontinuity. So now, you can take this x value and plug it in here. And there's your point. So we write, this is equal to negative 5. It has a limit. It has a limit. A limit you can see on your calculator, and you can find it algebraically. Sometimes we're going to reach things that we can't factor. That gives us an asymptote. An asymptote I can't remove. And then it will have no limit. Here's one. You can confirm it on your graph. You can factor this if you like into your perfect square factors, or group this guy actually. You can group this. So now you can take out 1. You can factor this again if you want to. So this point is removable. Okay. And x plus 1. Sorry, x plus 1.
X squared plus 1.
I knew I did something wrong here. Okay. Thank you. So when you remove this, otherwise if this was a minus, we'd still have a problem here. So keep the plus in there, and then if you plug in this value now, you should be able to return a point, which you also can check on your calculator. Now where does it converge? At the 0.5 or the 1.5. So you can confirm this algebraically as well as graphically. It's hard on your graph sometimes without looking at your table, because on your graph it looks like a continuous line. It runs right over your point of discontinuity. It can't, if you remember back when we did this, it can't show you that little point of discontinuity. But in your table at 1, it says error. It says can't use it. So it has an error in here. Yes. Because you factored out a 1 out of here. I had my line too close and I didn't see my plus. Because this factor is the same as this, right? So what's left? X squared plus 1. Just group it. So you've got 4 things. Whenever you have 4 things, group them like this. What can I factor out of here? X squared. What am I left with? X minus 1. Now, normally I can factor something out of here so that it looks exactly the same, but it already looks the same. So what's in front of here? A 1. So it looks like this. Here's my common factor. If you took this away, what's left? X squared plus 1. Okay. Now, the rationalization one, this one works just a little bit differently. If you notice where your radical is, it's in your numerator. So this one we're going to do a little bit differently. If we try to plug a 0 in here, what would happen? Undefined. So we know we have to eliminate that denominator somehow. So we're rationalizing from the numerator. And you rationalize 2 terms by taking its conjugate, making it a perfect square. So what you multiply on the numerator, you have to multiply in the denominator. Use the conjugate. And you can graph this as well. It looks horrible as a graph. I think this is what the graph looks like. I don't have the graph. It looks terrible as a graph, but you could see in your thing, this is going to say error here. This is where and you can try to plug the 0 in. You have no place to put this in. So when you rationalize this, you're rationalizing your numerators. God bless you. So if we do this, these are your perfect squares. So a radical times radical is just going to pop right out. Negative 1 times positive 1, negative 1. Now, don't distribute the bottom. Our goal is to get rid of that x, because the x is giving me trouble. Just put it here. That's why it's not as bad as it looks. Put it here and just slide this over. Don't distribute this yet, because you should be able to, in the numerator, eventually cancel that x out. So plus 1 and minus 1 cancel out. Now what happens to your x's? They cancel out. What's left in your numerator? 1. And I don't care what's left in my denominator, but now I should be able to plug a 0 into here. So 1, if I plug a 0 in, square root of 1 is 1, and 1 plus 1 is 2. So my limit, as x approaches 0, my y value, if I could fill in that little dot, would be at positive 1/2. And if you looked at it graphically, isn't it converging at the 1/2, 0.5? So my graph also confirms it. They look really bad, but don't distribute the denominator. You made the top be conjugates. Conjugate says perfect squares. Multiply the first term, multiply the last term. The middle terms are gone. They cancel out. So just slide the denominator over, and you should be able to reduce that down. Okay. This guy, same thing. So if we put a 0 in here, could we actually use the 0? What would happen if we use the 0? I don't know what happened to this graph. It's actually two little things. I don't know where this red comes from. I just wanted to show you where the point of discontinuity was. But your graph does a horrible job with this because it can't get any closer to your asymptotes, don't forget. And we're going to hit those asymptotes again. But right now we're looking for this little point of discontinuity. So your graph comes closer to that axis, but just doesn't touch it until it hits and jumps over your 0. So if I put the 0 in here, I wouldn't be able to use this. So you have to rationalize this fraction. So how do I rationalize this? How do I get rid of this whole fraction thing? Let's put this over 1. What's your common denominator? So just give it to me in two sets of factors. 5. So 5 times 5 minus x. So put this on the top of every term. Just find out what factors you need. And now cancel these guys out. 5 times 1 gives me 5. 5 comes out. Be careful of this minus sign. Nothing comes out of here. So I get 5x. Now, resolve your numerator. Out comes the 5 minus 5. And don't distribute your denominators until you see what you could reduce. Because if you distribute it, you're just going to have to factor it back out again to be able to reduce anything. So now when we reduce this, we can take out your x. What's left in the numerator? 1. Now you can leave this like this, or you can distribute it. Now it doesn't matter. If it doesn't buy you anything, I wouldn't even bother distributing. I would just leave it like this. So now, let's see if we can plug a 0 in here. So if I plug a 0 in for this, this gives me 5 times 5 minus 0 is 5. And this gives me my 0.04. And on your calculator, it should converge to the same point. If it's removable, if it's not removable, and we'll hit those. There'll be jumps, there'll be asymptotes, there'll be things we can't eliminate. We just see them in different forms. But we call them your points of discontinuities when we did these guys. Now, this last one, is it the last one? I think this is the last one. A nice little piecewise function. And you want to find, I didn't give you a limit to do. So let's find out where it approaches as the limit approaches 1. And I want to see what happens to 1. So 1 is deciding this guy is the parabola for anything that's 1 and below, but it's closed here. This guy is the 1, but it's open here. So remember your piecewise. Does this meet at the same point? Could we fill in one point? Can we find one y value to connect that little line? So the limit does not exist. Your limit does not exist. If it did, we would be converging back to the same number. And sometimes that happens. Sometimes when we have a piecewise, they both meet. One's open, one's closed. It's still a function, but we don't meet at the same end. So, I mean, these are things we've already done. We've seen these before, right? Nothing was new that we did today. We just called them using your limits. It's always nice to look at the graphic part of this. I like to see it in the graph too. See where they converge, see where the error is, see if your error shows on your graph. If it doesn't, then you know it's going to be removable. If you see your graph jump over, you know, like it's not converging, it's like a step graph or something, or it's not meeting at the same point, you know your limit is not going to exist. So these are